Hi, in this course we will talk about an introduction to reinforced concrete. So we'll go to the definition, the loads, the load combinations, the ACI code, some basics and basic principles of reinforced concrete design and so on. So first of all, the definition of reinforced concrete or reinforced cement concrete. So it is a combination of concrete and steel bars, which are the reinforcement bars here in this image. The main concrete properties, first of all, the workability. We have a slump test that measures the water to cement ratio and measures also how the concrete is workable in the workplace, in the field, okay? The strength. Strength is an important property of concrete because this is why we add the concrete to, because it is strong in compression, but it is weak in tension. So we add cement or concrete because it resists the compression forces, and we add steel bars because they are strong in tension, so they can resist the tension forces. So the combination of those two material, concrete and steel, becomes make the purpose. The third one is the durability, which means the concrete should be able to resist the changes in the climate change. Okay, the changes of it is volume and the weather conditions in general, like temperature and so on. Creep. When a sustained loading applied for a considerable time, this maybe will become an failure of the structure because there are a sustained loading and the concrete is overloaded for a considerable time. So the strains will become large, and therefore in this image we can see the creep, and this may become a failure. The shrinkage. Shrinkage means the concrete should be able to the reinforced concrete should be able to resist the temperature changes. So in this image we have a problem of a shrinkage in this concrete. Maybe is it due to less reinforcement than the minimum. And shrinkage reinforcement, there is an equation, we will talk about it later. There is an equation to find the minimum reinforcement ratio to resist temperature effects or the temperature effects due to increasing and decreasing of concrete volume. Unit weight of concrete is very important because it is crucial in loading calculations, and the structure has its own dead load. So we need to compute the dead load and to add it in consideration in load calculations to do the further analysis and so on. The modular ratio, or it is called the modulus of elasticity or modulus of resilience. It is related to stress strain diagram, okay, to the steel and the concrete. The Poisson's ratio, which is very important property in thermal expansion, and to understand how the concrete is will work when there are thermal expansion. And an advantage of concrete, it is good in fire resistance rather than the steel bars, which are not fire resistance, okay, which are not good in fire resistance. The main reinforcing steel properties are high tensile strength, as said, and they are low in fire resistance. Why we add reinforcement or steel bars? Because they are good in tensile strength. Concrete don't have the ability to resist the tensile stresses, but it is good in compression. The concrete compressive strength, which called F prime C or FC prime, is based on using uniaxial compression test, which is about 150 millimeter diameter and 300 millimeters height concrete cylinder, is tested after cured under standard laboratory conditions and tested at a specified rate of loading at 28 days of curing. From this test, the stress strain curves of concrete cylinders are obtained. Here we have in this image the cylinder there, and in some cases and some regions like in Palestine, we do a cubic specimens. Okay, they are 10 by 10 by 10 centimeters, or some regions use 15 centimeters. But the ACI code is based on cylinder test, and this is the dimensions of this cylinder. It is 15 centimeters diameter and 30 centimeter height cylinder, and it is and the FC prime is recorded after 28 days of curing of this specimen. Concrete stress strain diagram. The first portion of this curve we have C in the y-axis the stress and the x-axis the strain. So if we have this cubic or cylinder specimen, and we applied the stress, the normal stress, by the compression machine, and we recorded the strains of this specimen vs the stresses. Okay, we can have this curve. This is the ultimate stress value that the cubic or the cylindrical specimen can carry. So it is capacity. It's called FC prime, or compressive strength of this concrete. The first portion of curve is to about 40% of the ultimate strength FC prime. It can be considered as linear. In this case, or in this region, it is elastic because it is linear. Okay. After this point for FC prime, the stresses becomes in other case, the lower of strength of concrete generate will be the failure strain. After this will be have a crushing stage, and then will we have a failure. Okay, we will have a failure. The steel stress strain diagram. If we applied a rod or a rebar, and we measured the strain over the stresses, and here are the tensile stresses, not the compression stresses, because we are interested in tensile capacity for the rebars. And we can see here we have linear elastic up to the upper yield point. At this point we will have another stage which is yielding, when the formation will be larger. And this is the lower yield point. We have an upper point and lower point, and then we will have the yielding, large deformation, and the strains in the rebar will become available. And then we will have a hardening, okay, a strain hardening up to the ultimate tensile capacity, right there. And then we will have a nicking of the rebar until the failure or the fracture will be occurred at this point. So this is the test, the tensile strength test of steel. We have here the rebar, and we have this, and this is the diagram that is printed there, which is the stress strain diagram. And this device is measuring the strains there and the deformation delta L over L, okay, over L for the specimen, and already recorded the stresses at each point and each strains, and then it is printed at this machine. The minimum concrete compressive strength according to ACI code. The minimum compression strength for the concrete is given by, first of all, if it is a special moment frame for seismic design and special structural walls, which mean we will have a high ductile members with the grade 60, which is 60 KSI, or 80 KSI reinforcement. Therefore, FC prime should be greater than or equal to 21 megapascal. Okay. By the way, the FC prime for cubic 10 by 10 by 10 centimeters dimension specimen is equal to 0.8 the FC prime of cylindrical test. Okay. So in this case, we are talking about cylinder. According to ACI, it is considered for a cylinder specimen, not a cubic. So FC prime should be for special moment frames greater than or equal to 21 megapascal. And also for special structures wall, high ductility members with the grade 10, 100 reinforcement, 100 KSI reinforcement should be FC prime more than or equal to 35 megapascal. The concrete modulus of resilience or elasticity in the linear curve, in the linear stage of the stress strain diagram, EC for the concrete here, it's about 4,700 square root of FC prime. Why that? Because we have this equation from ACI code, and it depends and varies with the time. Okay, it depends and varies with the time. This factor EC, and these are the equation in general. EC is equal to 0.043 omega C to power 1.5 square root of FC prime. Okay, FC prime is the compressive strength. Omega C is a concrete density in kilogram per meter cubic meter, and it is various between 1,440 to 2,560 kilogram per cubic meter. So yep, if we take an average and if substitute 2,300 kilogram per cubic meter, then we will evaluate the EC to be this equation, 4,700 square root by FC prime. Okay, so this is the EC that we will use in the design later. The concrete tensile strength. As we said, concrete is good in compression, but it is weak in tension. The tensile strength of concrete is relatively low, so it is approximately equal to 0.1 FC prime based on the ACI code 209 or 92. The tensile strength for pore tension is given by this equation: Ft, T for tension, and F for sigma or the stress or the capacity is 0.33 lambda square root FC prime. By the way, lambda is just related to the type of concrete, and if it is normal, not lightweight concrete, it's normal concrete, so it's equal to 1, just a factor. So Ft in this case is equal to 0.33 square root of FC prime. The tensile strength of concrete can be determined using a split cylinder test, or is called indirect shear test. Okay, indirect shear or tensile strength test. Reinforcing steel strength. ES is regarding the steel rebars or rebar, okay, the reinforcement bars, which is the modulus of elasticity also, and it's equal to 200,000 megapascal. Steel grade 60 KSI. By the way, if you would like to make a conversion, or you want to convert the KSI to megapascal, you can multiply by 7. This is the factor for the conversion of KSI to megapascal. So 60, grade 60, which is widely used according to this specification, ASTM and ASTM, these codes. So we have the main difference between steel A615 and A76 is that the steel A76 is more ductile, and they both have the same yield strength. Grade 40 yielding strength, it's 40 KSI, which is 280 megapascal, and the grade 60 is 420 megapascal, and grade 80 is 560, and grade 100 is 700 megapascal. Okay, yield strength of undeformed bars is 250 megapascal. This is for the stirrups, okay, for the undeformed bars. This is grade about 36 or 40. Based on the ACI 318-19, the ratio of actual tensile strength to actual yield strength minimum 1 to 10 for steel A60, A6015, and 1.17 for steel A76. There are limitations on steel yield strength of seismic design, especially in special moment resisting frames, to provide ductility provisions, and you can refer to this chapter in the SI code. In steel bars, sometimes the ultimate strength of the steel is about 1.25 to 1.5 if yielding. Reinforcing steel bars. The bar area is given by AB is equal to pi over 4 dB square, where dB is the diameter bar in millimeters, bar diameter in millimeters, and AB is the area of the circular area, sectional area of this bar in millimeters square. If you would like to compute the bar weight mass per meter length, it's equal to bar area AB by 1 meter by the steel density. And then we can have we have here area and here meter cubic, so it will be kilogram over meter for 1 meter, and it's equal this equation. By the way, the density of steel is about 7850 kilogram, and therefore we have the final equation there, a quick equation to compute the bar weight mass per meter. It's equal to bar diameter square over 162 or 0.0062 dB square. By the way, bar diameters in millimeter are 32, 25, 22, 20, 18, 16, 14, 12, 10, 8, 6. Bar spacing and concrete cover. We have these covers or spacers. The cover is defined as the spacing between the wood or framework up to the outer edge of reinforcement. Okay, and this is very crucial in the design and the practical field. There are some plastic and there are some specimen of 2.5 centimeters. Bar spacing and concrete cover. The cover is used to protect the steel from corrosion, first of all, and this is very important. The concrete protect the steel from fire. Okay, concrete protect the steel from fire because concrete is good for fire protection, unlike the steel. So they are work together. Codes like ACI code specify a minimum required concrete cover as like that. In beams, a clear distance between parallel bars in a layer shall be not less than maximum of the bar diameter dB 25 millimeters and 4 to 3 times maximum size of aggregate. Okay. In beams shall not be less than 25 centimeter. In columns in a layer shall not be less than the maximum of 1.5 times the bar diameter 40 millimeters and 4 to 3 times the maximum size of aggregate. Generally, columns and beams are to be 40 millimeters clear cover, slabs and walls, joists and shells 20 millimeters for bars with diameter less than 35. Members cast against soil 75 millimeters. Members subjected to drink water 50 millimeters. Regarding the loads and how the load theory is, the load distribution theory. First of all, dead load is the own weight of structural elements, beams, columns, slabs, walls, etc. The superimposed load, it is just the weight of non-structural elements, just like the covering materials, mortar, tiles, partitions, and so forth. The live load, it includes the people load itself, furniture, machines, and other unfixed or movable parts. The snow load, for sure, in the roof load, in the roof slab. The soil weight, if there are a wall or a retaining wall, there therefore will be a soil weight. So it is included in the design. The water weight is just a very low value, but it is considered in the load combinations later. So it is water weight, a rainfall in the roof or on the slab. So we have here the loads, and they are just distributed in this slab, and then it will be moved in the beams. We have joists and beams there. The joists distribute and convert and transport the load from the slab to the columns. The columns are transferring the loads to the foundation, and the foundation are transferring the loads to the soil. The live loads extracted from the ACE 7-22 table 4.31. For building type, it's about 2 kN per meter square, a 5 if there are public rooms and their corridors. For office buildings, libraries, hospitals, garages, training rooms and restaurants, balconies and decks, schools, sidewalks, and stairs, etc. Design methods for the reinforced concrete structures. We have two design methods. One is previously used and it's used for the designing of water tanks. It is a working design method or allowable stress method. Allowable stress method. Use of actual working unfactored or surface loads. It use of allowable stresses in a concrete and steel as specified in these equations. Concrete allowable strength compression and compression is 0.45 FC prime. So we don't take the full capacity, we just reduce it by 0.45 FC prime. The steel allowable strength tension, it's also 0.4 F yielding. We are not taking the yielding because we are in the allowable or the elastic region, an allowable stress method. If you want to design on the stress capacity in the elastic or plastic region, so we will talk about another design method, which is ultimate design method. In this case, we use the ultimate loads, which means we use a load combinations, okay? And we magnify the loads by load factors or load factors and reduction factors, as well as to consider the material and eccentricity and so forth. But we maximize and we factored and magnified the loads, the surface loads. And we use section capacity, strength reduction factors as well as. By the way, the design strength is equal to the nominal strength by strength reduction factor like phi. So it's phi mn. Strength reduction factors according to ACI 318-19. 0.9 for flexural tension controlled, 0.75 for shear and torsion, 0.65 for axial tied column, 0.75 for axial spiral column, and 0.6 plain concrete, 0.6 for plain concrete under the footing and so forth. Other reduction factors are also in special cases found in the ACI code. What's the purpose of strength reduction factors? A, to allow slight variations of material strengths. B, to allow slight variations in dimensions, as well as the eccentricity, and to allow inaccuracies in the design equations. For example, the load combinations or the load calculations and estimation. C, to reflect the degree of ductility. We need some ductility for systemic design and special frames. D, to reflect the importance of the member in the structure. Purpose of the load factors to account for inaccuracy in load calculations, slight variations in loads during lifetime of the structure, variability in structural analysis. Lastly, the load combinations. Load combinations that combine the different main load in building structures. The wind and earthquake loads are calculated at ultimate load level. We have these equations, 1.4 dead. By the way, D for dead load, L for live load, LR for live load at the roof, S for snow load, R for rain load, W for wind load, E for earthquake load or seismic loads. And the second one, 1.2 dead plus 1.6 live plus 0.5 LR or S or R. And we have lastly here these equations. The primary load here, dead load, live load, wind load, earthquake, wind load, earthquake. And these equations are given in this table, and you can refer to this table from the ACI code. And in the design, we will design based on the envelope one. For example, if the M ultimate is equal to 200 kilonewton meter from this combination, and from this combination we have 250 50 kilonewton meter. So the envelope one will be based on this equation. So this equation or load combination is control the design.